Okay, so today we're going to do a review of solving systems of linear equations. And we talked about three different methods to being able to do that. We explored graphing, and then we did two algebraic methods, which included substitution and elimination. So today I want us to review those, okay? Make sure that we're comfortable with all those. And so to start our review, I want to turn us all to that very front page in your binders. Okay, so if you picked up a binder, this is the very front page. And what it does is just gives us a quick snapshot of all of the three different steps with all of the steps necessary to being able to complete those. Okay, so they give us an example. So I'm just going to kind of go over those with us to begin. So our first method was by graphing, and graphing is really nice because graphing shows a picture, right? And a picture is worth 1,000 words. So it's important that we know how to graph. Now, we will find out, or you found out that, with working through some of our application problems, that graphing wouldn't really be the most practical unless you had a computer to help you out, because graphing is going to involve you being precise, okay, like exactly precise. And so a computer or a calculator would help you do that. But how would you graph? So one thing that's awesome is that with graphing these, you're not learning anything new, okay, to start with. So all of the steps are going to be steps that you've already learned. So step one, you need to make sure that each of your equations is written in slope-intercept form, okay? So remember what that slope-intercept form is. Y equals mx plus b, okay? Those lines are very straight. Y equals mx plus b. So that's what we need to do first. So if we have our example over here, okay, here's my example, and I need to solve this system by graphing, you have to make sure that both of them are in slope-intercept form. It's nice, my second one already is, but my first one is not, right? You always have to make sure that the y is by itself. So we take a little time on step one to move that 3x over. And so when you do that, you subtract 3x's from both sides, so that instead you will be graphing, you will have that equation to help you graph, okay? So you wrote them both in slope-intercept form, perfect. Then the second step is just graph them, okay? Graph them how you would normally graph your linear lines, one at a time. So you'll first graph y equals negative 3x plus 2, okay? Now remember, whenever you're graphing in slope-intercept form, this positive 2 is your starting point on the y-axis, okay? You need to find 2 points. This will be your first one. So you notice I've got my first dot at positive 2, okay? And then from there, you use the slope, okay? Your slope, which is negative 3. And I'm gonna go ahead and write that as a fraction because that really helps me. All right, from my starting point, I had to move 3 spaces down and 1 to the right. So 1, 2, 3, and then 1 to the right. And there's my second dot. So all you have to do then is draw that line. Okay, and I know they already worked out this example. I'm just kind of showing you, hoping we all remember this. And then same here, I'll do the same exact thing, except I'll start at negative 4. And then my slope on this guy is a positive 3 over 1. So I go up 3 over 1. There's my second dot, and I draw it. Now, step 3 is the kicker. This is where we're going to find our solution. So how do you know, just by looking at the graph, how do you know what the solution to your system is? Well, you look for the point of intersection. Okay, so right there is where the 2 lines intersect. It's the only point that they have in common. So when you identify this point, you notice, where is it on the x-axis? Well, it's at 1. And it's at negative 1 on the y, okay? So my solution is 1, negative 1. So that is graphing systems of linear equations in a nutshell. So we'll have a couple examples of that in today's review. Okay, so now let's look at substitution. And so with substitution, this is an algebraic one. And so the motivation for us while we're trying to solve a system of linear equations algebraically will always be to somehow mesh the 2 equations together so that after you're done with that, you end up with only one equation with one type of variable, and then you're able to solve for that variable, okay? So that's what's stopping us right now, is that each one of my equations have two variables in them. So they gave a couple different examples for these. Maybe we'll just kind of run through one of them. But the first step that you want to do with substitution is make sure that one of your equations is solved for either variable. So you have to choose which variable you want to solve for. In both of these examples, neither equation is solved for a variable. So I'm just going to work on example 1, so we're not hopping around. But when you think about which variable should I solve for, x, that y, that x, or that y, be smart about it. Look for a variable that has a coefficient of 1, because those are going to be the easiest variables to solve for. Like here in this second equation, I have negative 4x plus y. I want to solve for that y because that will be easiest. So we do that. Negative 4x plus y equals negative 2. The only thing you have to do is move that positive 4x over, and it becomes a positive 4x. So you end up with y equals 4x minus 2, okay? All right, step 2, this is where it happens, okay? This is where the magic happens, where you substitute the equation you just solved for y. You're gonna substitute this expression into the other equation, okay? So I've got my other equation, which is 7x plus 2y equals negative 5. And this time, instead of y, I'm gonna make my substitution. I'm gonna substitute in 4x minus 2, okay? So after I plug in 4x minus 2, I end up with one equation with only one type of variable, an x, okay? So then we're gonna go through our steps to being able to solve an equation, okay? You guys have those down. Make sure you simplify by distributing, right? Combine those like terms, and then isolate your variable, and then you have found one part of your answer, okay? You found the x coordinate. So that was step 3, solve that new equation for that variable, okay? Once you're done solving, you have the x, but you still need the y. So what do? You can pick either one of your original equations. It doesn't matter, okay? But you're gonna plug that number, negative 1, back into there, okay? And then once you're done, you'll end up with y equals negative 6, okay? So here, they plugged it into this first equation again. I think I probably would have plugged it into that one. Maybe a little bit easier, but it don't matter. So that's the substitution. Look over this example and see if you can follow every step, okay? It's always good to be able to do the process, but then also to be able to read somebody else's work and say, okay, they did this and this stuff. They distributed, they combined like terms, they added, they substituted back in. So make sure you're going through those, okay? Okay, our final method was called the elimination method, and it was also an algebraic method. So the motivation behind it was that we need to somehow mesh these two equations together so that after we're done, we end up with only one type of variable, okay? Now, the first thing you always want to do is make sure everything's lined up, because how are we going to mesh it? We're going to either add it together or subtract it from each other, okay? So whenever we're adding and subtracting, just like back in math lab when we were adding any numbers, we'll make sure that we are lining everything up properly, okay? So in math, it's always good to find a way to be consistent, okay? So when I line my stuff up, I'm going to write it in a form that in math we call standard form. And maybe you've heard of it. Maybe we've mentioned it here or there to you. But all standard form is that, hey, I want my x's and y's to be on the left-hand side, and I want my constant to be on the right-hand side. So in both of these examples, let's see. In both of these examples, and the first example, it was not in standard form, okay? Everything wasn't lined up nicely. You see those equal signs? I got one here and one there. So they had to move the 9. They have to move the 9y over, okay? So in the first example, they did have to do a little maneuvering. In the second example, everything looked pretty nice, okay? So if you notice on the second example, step 1, there was nothing to do, okay? And sometimes that happens in math. We tell you the steps, but sometimes they give it to you nicely and you just don't have to do it, okay? All right, so my second step is that I need to multiply either one or both of my equations by some number so that I create common coefficients, but ideally I would like them to be opposites, okay? Why? Because adding them together will be a lot easier for us. So if we're already doing some multiplying, you may as well make it easy and make them opposites. So in the first example, I only had to multiply the second equation, okay? Because when I did that, I multiplied it by 3. My -3 became a -9, which then matched up with my +9, okay? So when you added those two equations together, the 9s went away, okay? And you were left with one equation with one variable, okay? So we're at the same exact point now as we were in our substitution, okay? Nothing is brand new anymore, okay? So we've got to solve for x. After we solve for x, then plug it back in, okay? Plug it back into one of those original equations. So walking through this example, we had to multiply both equations, okay? And why was that? Well, my coefficients weren't multiples of each other, okay? So here, and it's not lined up, so it's a little bit harder to see, the 9y and the -3, 9 is what we call a multiple of 3 because you can multiply 3 to get 9, okay? And here, neither one of those happened. 3 is not a multiple of 2. 2 times nothing gives you 3. 5 is not a multiple of 7. 5 times nothing gives you 7. So, or at least whole numbers, all right? So hopefully we're okay with that multiplying and why we multiply what numbers in which equations, okay? So the same exact process, after you add them together, you are left with one variable with one equation so you can solve, and then you plug that back into one of your old equations and voila, okay? So those are the 3 different methods used to solving a system of linear equations. And now at the bottom, they just kind of went over some of those different types of solutions that you can have. Okay, so most of the systems crossed, right? And they had one solution, or the lines crossed on the graph. So, but sometimes something funky happened, right? Like, remember the times when the lines were parallel and they didn't cross? So they didn't have a solution. So how can you interpret that? If I give you a problem and I say find the solution, how are you going to be able to tell me if there are no solutions? Well, graphically, if you look at them, okay, the lines are parallel. And so graphically, you can see that they will never cross. Now, we do know something about parallel lines though, okay? We know that their slopes are the same, right? They have the same slope. So if you look at your equations, it's not even necessary to graph necessarily, okay? All is necessary is to be able to identify the slopes. So with both of my equations, I want to make sure they're in slope-intercept form so I can identify the slope. Here, this guy is not yet in slope-intercept form, so they took a little bit of time to rewrite it, and we can identify the slope as being -5. On my second guy, it's already in slope-intercept form, and I can clearly see my slope is -5. So they have the same slope. So I have one of two things. They can be parallel or they can be the same exact line, right? And if they're the same exact line, they have infinitely many solutions. While if I have different y-intercepts, I know they're starting at 2 different places so that they're not the same line. So you either graph them or you can look at the slope and the intercept and be able to tell just right there, okay? Now, how do you tell when you're using maybe the substitution method or the elimination method? What happens? Well, whenever you do the substitution or you start doing the elimination, you don't just get rid of one of the variables. Both of the variables end up going away, okay? And what's left is a false statement. Maybe something silly like -20 equals -3. That's never going to happen. -20 does not equal -3. So I know that there's no solution. Okay, so similarly, if you're looking at, and so we would call this an inconsistent system. I don't think we went through that word, those words, but we call it an inconsistent system. Inconsistent means it's just doesn't have a solution, okay? Another one is called the identity. Now, when you think about your identity, okay, who you are, right? An identity is something that's the same. So an identity is when the system ends up giving you two of the same exact lines, okay? They're identical. So how can you tell if there's infinitely many solutions? Well, graphically, you could draw the lines, you could graph the lines, and they would end up lying right on top of each other, one and then the other. They're the same line, so there's infinitely many. Here, how do they do it? Well, they rearrange it into slope-intercept form, and they realized, hey, it has the same slope, it has the same intercept, this is the same exact line, okay? Substitution or elimination method, this would work. What happens is when you're trying to combine your equation, either using substitution or elimination, you end up eliminating both of the variables, okay? But in this case, you end up with a very, very true statement, like -28 equals -28, all day, every day, okay? So you would know that that's infinitely many solutions. So this sheet's really nice. It's taken all of our stuff that we've done in the last week and kind of put it nicely together so that you can kind of read through it. So whenever you're studying, reviewing, this will be a good place to look. So I hope this helps for you guys.